Okay, looks like we all successfully made it to school today. All right, well done. So today my plan is to do some problems in class, some that I walk us through to start, and then some that I'm going to let you guys work together. That very last page that has 4 or 5 problems on them, we'll try to do about 5 minutes on each of them to see if we can get through there. All right. I know that Jeremy had a good turnout at PASS yesterday, and I know that some people are still having problems with Connect loading for you. Okay, so I hope that those issues get resolved at some point today. Again, I changed the due date to the Connect homework till tonight at 11:30 p.m. If you're still having an issue with Connect and you've contacted Connect support, just let me know. Okay, I don't want you to sit there and watch it swirl at you for hours and make you want to throw your computer across the room. Okay, don't want that to happen. So please just let me know if that's going on. I will also make a ploy that if you're struggling with the problems that are there or you're having problems with the questions that we do in class today, please come talk to me. I have office hours today from 1 to 3. I'll make a plug for them. Right, I sit in my office for 6 hours a week just waiting for you guys to come see me. Okay, so I am more than happy to help you if some of these guys are giving you a run for your money. All right, but one question Jeremy did tell me that, and maybe giving you guys some problem on Connect, is when they ask you to solve for the Van Hoff factor, and it's either a little bit less or a little bit more than 1. Okay, and I wanted to, when we closed lecture on whatever day that was I last saw you on Friday, right, we were scrambling to get through this slide on the Van Hoff factor and the difference between strong electrolytes, non-electrolytes, and weak electrolytes. And that comes in here at the weak electrolytes. That question that could be giving you a hard time in Connect, right? Because a weak electrolyte only partially dissolves. Well, okay, let me say dissociates. I think they're spelled the same. Okay, and I wrote in the notes that that means the Van Hoff factor is approximately 1. Okay. If you are solving for delta freezing point or boiling point, you should assume that a weak electrolyte has a Van Hoff factor of 1. However, if you are solving for the Van Hoff factor, given a delta T, a molality, and a KF or KB, you're going to get that exact Van Hoff factor, okay, which may be slightly more than 1 or slightly less than 1. So I don't want you to panic that you're not getting exactly 1. Right? For a non-electrolyte, you should get just about 1. Okay, but there may be some slight dissociation that you're not aware that's happening. So don't freak out if that's the case. All right, so I left you guys here and asked you to try to get through this problem without me. So I'm just going to go through how I did this problem, and please stop me with any questions. Okay, this is so that we can really get a feel for how to attack both the concentration units as well as these changes in colligative properties. Okay, so I have a KB of 0.52. And essentially what I want here is what is my change in boiling point for this solution. Okay, so the first thing I'm going to ask us is what do we know? Okay, so what we know, okay, let's say things that we obviously know. We know the KB, okay, we have this percentage up here, okay. I'm going to write myself the formula for that change in temperature. Okay, so I know that delta T of the boiling point is equal to I molality times KB, or KBP. Okay. Do I have molality?
No.
No. Can I find molality?
Yes.
Okay, I'm seeing some things like this. And I'm going to make an assumption, which you guys are also going to want to do as you're doing any problem that has percent. Right? I'm going to assume that I have 100 grams of solution. And the reason I do that is to make the percent easy on myself. Okay? If I were to give you another volume there, you could multiply it by the percent and do it out that way, but if it does not say, you just want to assume that you have 100 grams. Okay? So the other thing I know is I know what the formula should be for percent mass. Right? So percent mass, right, is equal to grams of solute divided by the grams of solute plus the grams of solvent. Okay. So if I assume this 100-gram solution, how many grams of sodium chloride do I have? Okay, I'm seeing some mumblings of it. Okay, I get 12 grams. How are we feeling about that? Okay, then I get more like this. Okay. All right, so I have 12 grams of sodium chloride. All right, that's still my solute, so I put 12 grams sodium chloride in the denominator. How much water do I have? 88, right? I assume that I have 100 grams of solution. So if I have 12 grams of salt, that means I have to have 88 grams of water. Okay. So the other things, all right, I'm going to define what I know on this side. Do I know what I is for sodium chloride? All right, what do we think about holding up numbers with our hands? 1, 2, 5. Okay, I'm seeing some 2s. All right, peace to everybody else out there. Okay, the Van Hoff factor is 2. Right? Is sodium chloride a strong, weak, or non-electrolyte? Strong. Yes. Okay. There's another way to think about it. Does sodium chloride completely dissociate in water? Yes. Okay. So let's think about it this way too. If I have 1 mole of sodium chloride, how many particles do I have when it dissolves? 2, right? Perfect. So that Van Hoff factor, all right, is 2. Okay, and again, the K of the boiling point is given. So, okay, sorry, this is really twisty today. Okay, so what's, right, I have KB. So what's the only thing missing? Right? Okay, so what we want, right, is we need to find molality. That's the only piece that's missing from this formula. Okay, and my unit, right, I always like to write out what the definition of that is. It helps me see what I need to solve for. Right, that's moles of solute over kilograms of solvent. Okay. All right, can I solve for moles of sodium chloride?
Yes.
Okay, look at this. I'm getting some nods, all right? This is a good thing, right? I have that 12 grams. So I can take my 12 grams of sodium chloride. I can convert that to moles. Okay, and I got 0.205 moles of, not potassium, sorry, sodium chloride. Okay, so that's going to go in my numerator. Okay. How about in the kilograms of solvent? Do I know what that is?
Yeah. Yep. Grams of water.
Right? Hanging out right here. So that comes down here, but it has to be in kilograms. Right? So that becomes 0.088 kilograms. Okay, again, if that unit conversion's giving you a hard time, right, you want to know that there's 1,000 grams in 1 kilogram. So when I do that calculation, I get 2.33 molal sodium chloride. Okay, so now I have molality, I have the Van Hoff factor, and I have that KB. So I'm all set. Yeah.
The formula we used, does that find delta T or T boiling point?
Okay, so the question is, does this formula give me the actual temperature of boiling or the change in boiling point? Okay, and it is a delta T, so that is a change in boiling point. Okay, so if I do that, right, if I get a delta T, which is going to be equal to 2 for that Van Hoff factor times 2.33 molal times 0.52 degrees C per molal. Okay, my molals cross out. I'm going to be left with a degrees C. Okay, so my delta T in this case is equal to 2.42 degrees C. Okay, but I'm still not done. Man. Okay, I'm looking for the boiling point of this sodium chloride aqueous solution. Okay, what's the regular boiling point of water in Celsius? 100 degrees, absolutely. Okay, so let's try our first clicker question here. Okay, so I'm going to have boiling point is 100 degrees C. All right, and so answer A will be if I do a plus. Answer B is whether I do a minus sign here for my 2.42. Okay, let me click here before. Right, so do I add or subtract that delta? All right, chat with your neighbor if you don't feel good about it.
Whether a solution or a pure solution pure versus a solution.
Okay. All right, let's see if we can make our final answers, right? Are we adding that delta T or subtracting it? All right. Okay, so we're about 70% adding it, which is the correct answer. Okay? We do want to make this an addition. Well, maybe I'll do it in red. Okay. Because that old saying is boiling point, elevation, freezing point, depression. So when I get that delta, I really do need to be thoughtful of, number one, what the heck was the starting boiling point or freezing point? Any aqueous solution for boiling point is going to be 100 degrees C, and for freezing point will be 0 degrees C. So don't worry that you needed to remember some random value of freezing point or boiling point for a particular solvent. If you're doing something other than water, that standard boiling point or freezing point would have to be given to you. Okay? So that's good. All right, so let's think about now, see, I'm going to get all these to pop up. Okay, so what I want us to think about, and again, I want you to, maybe we'll do the first one and then see how we do and chat about what's going on, okay? So talk with talk with your neighbor and think about which one of these, okay, 1 mol ethanol, 0.5 mol potassium sulfide, or 0.8 ammonium chloride. Which one of those is going to have the lowest boiling point, which would mean the smallest change in boiling point? Okay, so chat with your neighbor, think about it. Think about what a small change means. All right, in that debate, be thinking about what is influenced in that formula for delta temperature of either boiling point or freezing point. But right, we're talking about boiling here. Think about what's in that formula. All right, so let's see how we did, and then we'll talk it out, okay? Okay, so we're going about 50%, 57% B. Okay, the correct answer is A. Okay, so let's think about this, because that means, right, obviously we're having a confusion moment, and that's okay, right? We're here to work those out. Okay, so if I know, I'm just going to write delta T, okay, because it doesn't matter as we talk about this whether we're freezing or boiling at the moment. Let's take that out of the equation. Let's just think about the change in temperature. Right, so my change in T is I, whoa, sorry about that line on the bottom, times molality times a constant. So one of the questions is, does that constant change between A, B, or C? Right? Every one of them is aqueous, which means that that K value is going to be the same for each of those solutions, which means we can take him right out of, we don't even worry about him. So now I'm just focused on what I times M is. So let's think about that for A, right? If I think about I times M, what is I for ethanol? Okay, does ethanol, is it a weak electrolyte, a strong electrolyte, or a non-electrolyte? Okay, if it's a non-electrolyte, all right, let's see by hand numbers, okay? How many is it? Okay, I'm seeing a lot of, I'm seeing a lot of ones, right? If I am a non-electrolyte, right? Ethanol does not dissociate in water. It is soluble, right? Alcohol is soluble in water, but it does not dissociate. You don't get a bunch of carbons and hydrogens and hydroxides floating around, okay? So that means, right, I have 1 times 1, which gives me 1. Right, we're on board with A? Okay. How about if I, again, am thinking about I times M, when potassium sulfide goes into water now, how many particles do I get there? All right, am I bold enough to get a show of hands with fingers? I feel like I'm taking a vision test up here. It's good if I can see all the way to the back. Okay. 3. Okay? Right? If I'm thinking about solubility rules, right? Any metal in group 1 is going to have complete solubility. So that's going to give me 3 times the molality, which is 0.5. Okay, so that gives me 1.5. All right, and how about C? If I'm doing I times M, does ammonium chloride dissociate?
Yeah, it's like
Okay, yes, ammonium, right, is one of those polyatomic ions. Right, and all chloride salts are soluble. So ammonium chloride, now does the NH4 break up? No, right? He exists like NH4 plus and you get a Cl minus. So now you have 2 times 0.8, all right, which gives me 1.6. All right, so now let's think about that first one again. If I have the lowest boiling point, right, I'm starting with 100. So my smallest delta will give me the lowest boiling point. Okay, who will give me, let's say, the highest boiling point? Let's give that a whirl now. I know that doesn't say that on there, but now that we've written these guys down, who will have the highest boiling point? Okay, I feel like maybe we're feeling better about this one. Okay, so let's see what we got. Try to get to 112. Ooh, some last minute answers. All right. Okay, that's awesome. Okay, because our highest boiling point is going to be the largest change in temperature, which has to do with that molality times Van Hoff factor being the largest value. So is our highest boiling point answer, is that the same as our lowest freezing point?
Yes. Because it's the greatest delta.
Yes. Okay. Because that's the greatest delta. Okay. So the greatest delta will give you the highest boiling point and the lowest freezing point. Because when we do that final solving for the temperature, right, that value, that delta is the same. It's whether we're adding it or subtracting it. All right, so now the last one here. Now we want to think about vapor pressure. Okay. So which one has the highest vapor pressure? Okay, chat amongst yourself. This one is the most challenging. Okay, think about what a high vapor pressure means. Okay, there are multiple ways to think about this. Well, we want to use our tools to make some educated guesses. Okay. Well, what is vapor pressure? Also think about what vapor pressure has to do with boiling point. They count that you try. They count that you try. That's the point, right? We're trying to think about them. There's like a, if so many questions were asked during the day, it's like if you answered half of them, then it counts.
I was watching the election video on Friday, and I was watching it the first time, I only let like one away, and then people started getting.
All right, let's see what we thought here. Okay, so we're torn about, almost 50-50 between A and C. And that's probably because we're trying to decide if high vapor pressure means increasing the temperature or lowering it, right? Because those are the sort of the two answers we went with. Okay. So the correct answer is A. All right. Now, let's think about it. Okay. There are, right in the shoe. Oh, you got it.
Oh, sweet. I got it.
That vapor pressure is the pressure of the gas above the liquid, or the solution in this case. Right? So we have all of these solutions: ethanol in water, potassium sulfide in water, and ammonium chloride. And the stronger the interaction between the solute and the solvent, okay, the lower the vapor pressure. All right, let's say that one again. Okay. I want to think about water molecules escaping from the liquid phase into the gas phase. Do I do that more easily if I don't have people hanging on to my feet? So I want to think about it kind of like that. All right, and this could be a bad, mob reference that, you got to tie concrete blocks to someone's body you're trying to get rid of, right? If you want to keep them at the bottom of the river. Okay, you want to increase their interaction with the water. So if I increase that number of particles, I essentially am weighing down the water molecules in the solution. Right? Because now I have an increase in intermolecular forces and I can't escape into the vapor phase. Right? So half the battle is thinking about what is going on with the vapor pressure as opposed to what that does to the boiling point. Right? So the higher the vapor pressure, do we think that has a lower or a higher boiling point? Oh, sorry, this is probably my aunt calling now. Okay. I have family that's driving from North Carolina. My family from New York State. I'm like, North Carolina says they're in a state of emergency. I know there's no snow, but just stay there because people, get on the roads and they get crazy. But anyway, so again, do I have a lower boiling point or a higher boiling point?
You have a higher boiling point, that means the interaction is stronger.
Okay, if I have a higher boiling point, that means the interaction is stronger, which means the vapor pressure is what?
Weaker. Lower.
Lower, right? Okay, because you want to think, and it's really, I will give you guys this to pat yourselves on the back. Wrapping your head around vapor pressure is the most difficult part of colligative properties. Okay, because you see it one way and then your brain thinks about it the opposite. Okay, so if you're struggling with that vapor pressure, that's okay. All right, you just want to kind of talk to yourself and think about, okay, vapor pressure is that going into the gas, all right, and what does that mean when you're trying to get into the gas phase? And also keeping in mind that the vapor pressure has to equal the atmospheric pressure for something to boil. So if you reduce something's vapor pressure, you have to put more energy in for it to boil. Right? That old adage, salt water does not boil faster, it boils at a higher temperature. Okay. All right. So I want to just briefly tell you guys, because I think it tells you something in Connect about osmotic pressure. If you have to use that formula for a calculation, that's fine. On an exam, I'm not going to ask you to do an osmotic pressure calculation. I might simply ask you a general question about osmotic pressure. Okay, there's a lot of things that use osmotic pressure to determine molecular weight of large biomolecules and polymeric materials, so it is very useful for a technique. But what happens is you have either a U-tube or some type of piece of glassware that has a semi-permeable membrane in the middle of it, where I have pure solvent on one side and a high concentration of a solution on the other side. And what happens is you get diffusion of those pure solvent molecules across the semi-permeable membrane to reduce that concentration. And when that happens, you push that side up into the tube. And what you do is that osmotic pressure is measured as the force that it takes to push that guy down. So the thing you kind of want to remember about osmotic pressure is that you are measuring the pressure caused by diffusion of pure solvent, which in most cases is water, across that semi-permeable membrane to reduce the concentration of your analyte solution, I'll call it. Okay, but again, if you have a problem in Connect, use this formula. Okay, we have molarity. We have the ideal gas constant and the temperature, as well as that Van Hoff factor. Okay, and big pi, as it usually looks, is that osmotic pressure. So all of those values would have to be given to you. Okay, so what I want to do, if this will let me, is, okay, let's go back, because again, understanding colligative properties at heart is understanding intermolecular forces. So I just want to make sure we're still feeling good about those. All right, so let's try some quick clicker questions here. So I have two beakers on the bottom. One is water, one is benzene. Okay, A is water, B is benzene. So I'm going to try to come through 1 through 6 here. So my first choice is ammonia. Who is he going to be more soluble in, water or benzene? Okay, in all cases, I'm looking for the more soluble in. All right, so let's try to get our final answers in here. Okay. All right, so I got 3/4 water. Okay, water is correct. Okay, ammonia is going to be more soluble in water. All right, and so now let's look over here at my list of intermolecular forces. Now I know, right, everybody has dispersion. So I'm going to just not think about dispersion unless it's the only one. Okay. What's the driving intermolecular force that makes ammonia more soluble in water than benzene? Okay, again, you're more than welcome to talk with your neighbor.
Yeah.
And also, like, dipole you asked for the strongest, right?
Yeah. It's in phys chem.
So pretty.
It's on the very upper top right corner of phys chem.
I know who's over. Do you know the number?
3210. No, 3220. Doesn't matter. If you get to the, no, that's a lie. 3120.
Okay. We get one of those.
All right, let's see how we did here. We'll get some last minute responses. Maybe. Did I? Oh, I freeze this. Okay. 80% hydrogen bonding. High five, okay? It's totally hydrogen bonding. Now, okay, dipole-dipole, in theory, is not wrong because there are dipole-dipole interactions. However, the strongest type of intermolecular force we have here between the two is hydrogen bonding. Right? I'm attached to a nitrogen, and water, the hydrogen is attached to an oxygen, so I can have hydrogen bonding between the two. Yeah. Is ammonia ionic? No. Okay, ammonia is not an ion. Okay, ammonia has a lone pair, which makes it polar. So ammonia is a polar molecule that is capable of hydrogen bonding. Okay, ammonium, right? So if I put another hydrogen on there, that becomes a cation, and then I could make ionic bonds with, say, chloride anion.
So if that were ammonium, was the strongest being ion with hydrogen?
If it was ammonium, it would be ion dipole. That's 100% correct. All right, let's try carbon tetrachloride. Okay, CCl4. More soluble in water or more soluble in benzene? Okay, let's see how we did on carbon tetrachloride. Okay, benzene, almost 90%. That's great work. Okay, because carbon tetrachloride is nonpolar, therefore it should have the largest solubility in the nonpolar solvent. Right, for my like dissolves like. And that only intermolecular force that this guy has is dispersion. Here's another question, just to mix it up. Does carbon tetrachloride have polar bonds?
Yes, but it's not a polar molecule.
Yes, right? So you can have polar bonds, but be a non-polar molecule. All right, you want to be careful about that. And here in NH3, it's that lone pair that makes him polar, because that lone pair is a serious bully when it comes to electron density, and that inherently drives the formation of a permanent dipole. Okay, let's try chlorine gas. Okay, so chlorine gas, is that more soluble in water or benzene?
CL2 doesn't have any
Okay, we're almost to our 120 mark. Okay, let's see how we did. Okay, we're a little less sure this time. Okay, is chlorine gas polar or nonpolar? Nonpolar. So if he's nonpolar, right, he's much more likely to go in to benzene, because benzene is nonpolar. Okay. So now let's mix it up here and say, okay, oxygen gas is oxygen gas polar or nonpolar? Nonpolar. Okay, so in our list here, Oxygen, chlorine, and carbon tet are the 3 nonpolar molecules. But of those 3 nonpolar molecules, which one do we think is the most soluble in water? Okay, so let's make carbon tet A, chlorine B, and oxygen C. Okay, which one is the most soluble in water? Okay, so think about what type of intermolecular force is that and the difference between oxygen, chlorine, and carbon tetrachloride. I think Jeremy likes this question. He's nodding his head at me. I don't know. Okay, talk amongst yourselves. See what you think.
I don't know.
I put C4 because it don't have any intermolecular forces between solute and solvent. So the one that has more dispersion, or like the most dispersion. So that would be the biggest one. It's just the biggest one.
All right, let's see if we can get some last minute answers in here. All right, let's see how we did. Okay, so I'm going with the majority of people saying oxygen is the most soluble in water. Okay, now before I give you the right answer, okay, or tell you what the right answer is, I want you to think about now which one of these intermolecular forces, A through E, okay, again, there may be more than one, but they're ranked from strongest to weakest. What is the strongest intermolecular force happening between these nonpolar molecules and water? Okay, so think about, again, talk with your neighbor, think about which is the strongest intermolecular force happening here.
Which one of the 3 you just listed?
Which one of the 3 that we just answered? Yes. I mean, they all have the same strongest intermolecular force. Any of that, when you're thinking about them, which force is dominating, okay? Right? That is not to mean a trick. They all have the same strongest intermolecular force. Okay? This may contradict the answer that you gave in the first place, but that's okay. That's kind of what I want to happen. Okay, let's see. Let's see what we thought about this guy. Okay. Okay, D, that is true, 100% true, because I have a nonpolar molecule, in each case, carbon tetrachloride, chlorine gas, and oxygen gas. Okay, they're all, so they're the induced dipole, right? And water is the dipole. Who has the largest induced dipole? Okay. What do we know about inducing a dipole, right? The fluffy atom dance, okay? It works as a fluffy molecule dance. If I get some volunteers to stand up here with me and look ridiculous, okay? So if I do a better job inducing a dipole on something that's larger, that means that carbon tetrachloride should be the most soluble in water. Okay? And maybe that's a trick question, right? Because you're like, obviously it's oxygen, right? Obviously, because all of our water has dissolved oxygen in it, okay? And that's something we can wrap our heads around because we really would never want carbon tetrachloride in our water. Okay, that's like drinking liquid cancer It is really terrible for you. Carbon tetrachloride, I think now is banned in Virginia. You cannot order it. It's banned in a number of states. It's really terrible for you. So we would never want it to dissolve in water, but it is soluble because of its polarizability. It is significantly larger and way fluffier than O2, right? And it's saying something at me. Okay. And in actuality, why does it always scan when we're in class? Whoever has class 3 hours later gets it. Yeah.
When you say fluffier, are you referring to like a molecular weight? Or?
Okay, so when I say fluffier, am I referring to the molecular weight? In general, that's a good rule of thumb. Yes. Because a larger molecular weight implies you have more electrons and you have more space to distribute that charge. Okay. Now, if you have two things that are the same exact molecular weight, the shape of the molecule then comes into play. But for us, in this particular case, we're thinking mostly about the molecular weight. But yeah, that's a great question. Question?
What about like cations being smaller than anions? Does that have anything to do with how its electron density?
Okay, so what if I'm comparing cations to anions and I isolate them? You know, like are cations in general more soluble than anions? And the answer is yes, you can use size there because you are distributing the charge, but usually you have the pairs of cations and anions in solution together. But if you were looking at them just individually, that would be something to take into account. Okay. All right, so are our thoughts on intermolecular forces getting better or worse as we do these? Worse. I hear someone else. Okay. I kind of like this sheet as a way for you guys to work together even outside of class and ask yourself different questions with respect to the solubility in these different solvents, okay, as well as the intermolecular force. Okay, I did have a whole sheet of problems for us to do. Okay, and what I'll do is I will try to post the answers to these questions, but I really would like you guys to give them a whirl, okay? Or bring them and come see me. My office is in the Phys Chem building, right, which is the one that perpendiculars the long ISAT building, in the upper top right corner. Okay? All right. Enjoy the pseudo cold / snow we have outside.